to the second session on galvanic cells. In this class, we will be seeing what are reversible cells and the reversible electrodes constituting the reversible cells. So, let us see what do you mean by a reversible process. Only then we can say what is a reversible cell. A process is said to be reversible only if the system, after undergoing some of the changes, should be restored back to the exact initial state. Only then we can say the process is a reversible process. So, it should return back to its initial state, that is very important. Now, so a reversible cell also should be in such a way, that is, it should be reversible. You can say that it should be reversible. A cell that satisfies the thermodynamic requirements of reversibility, we call that such cells to be a reversible cell. Okay. Now, the condition for reversibility in thermodynamics is that the driving force which performs the action should only be infinitesimally greater than the opposing force, and also it should be possible to reverse this process by just applying a force slightly greater than the one acting on it. If these two conditions are satisfied, we can say that process is thermodynamically reversible. So, when there is a driving force, it should be only infinitesimally greater, and again if you have to reverse it, you have to give a slightly different greater force and the process will be reversed. Now, when we consider an electrochemical cell, the conditions are slightly different because we are concerned with the potential developed in the cell and the cell reaction occurring within the cell. So, here we are going to see what do you mean by a reversible cell. A cell is said to be reversible. The first condition is if it is connected to an EMF. EMF means a potential which is exactly equal to the cell potential. So, here we are going to connect the cell to a potential which is equal to EMF of the cell. Now, what happens is no current should flow through the circuit. So, this is the condition. I will just show that condition, that is first condition is, that is external EMF is equal to EMF of the cell, that is the first condition. Now, under this condition there is no flow of current. Okay. Now, what I am going to do is, I am going to make the external EMF slightly smaller than the EMF of the cell. Okay. Once the EMF of the cell is greater than the external EMF or external EMF is smaller than the EMF of the cell, what happens within the cell? Now, there will be an amount of current flowing out of the cell. So, you will be getting current from the cell to the external EMF and there will be a cell reaction going on within the cell. Okay. So, that is the second condition is that we are having, that is external EMF is less than EMF of the cell. So, this is the second condition and current is flowing from the cell to the external circuit. Now, we are going for the third condition. If the external EMF is slightly greater than the EMF of the cell. Now, here the process will be reversed, current will be flowing from external circuit into the cell and there will be a cell reaction occurring within it which will be exactly reversed. So, the third condition we are taking is the EMF external is greater than E of cell. Okay. Now, I am going to give some example for a cell reaction. Suppose the cell reaction is A plus B giving C plus D. Okay. So, if external EMF is equal to EMF of the cell, what will happen? There is no current flowing through it, means there is no redox reaction taking place. So, no reaction will be taking place within the cell and no current flows out of it. Second condition is the external EMF, it is less than EMF of the cell, or you can say that potential which is in the external circuit is lesser than the potential within the cell. So, what will happen is the current flows from the cell to the external EMF and the cell reaction taking place will be A plus B giving C plus D, and this is the redox reaction. It is an imaginary redox reaction, that is A plus B giving C plus D. Okay. Now, we are going to consider the third condition where the external EMF is greater than EMF of the cell. Here current will never flow from the cell because external EMF is greater. So, the chances is, that is, the current flows from external circuit into the cell. Now, what happens is, during this process you cannot have the reaction A plus B giving C plus D. Instead, you get the reversed form, that is C plus D gives A plus B, and this is what should happen if the cell has to be reversible. That is, if current is flowing out of the cell, there should be a particular redox reaction taking place, and when cell is having a EMF lesser and if current is flowing into the cell, the redox reaction has to be reversed. So, we can call such a cell to be a reversible cell. Only those cells which satisfy this condition, we can say that cell to be a reversible cell. An example for a reversible cell is a Daniell cell. Daniell cell, you can do one thing, you start the cell, you draw energy, electrical energy from that, and after some time when the electrolytes are being consumed, when the potential drops, you supply an external potential, you can revive the cell because the reverse reaction takes place. You have charging batteries. What happens there? That is, when we draw the current, there will be a certain redox reaction occurring there. When you charge it, it is going to get reversed and you get back the battery into proper working condition. But one thing you should understand, there is no 100% reversibility. Okay. Now, let us see what you mean by an irreversible cell. Irreversible cell is a cell which does not obey any of these conditions. So, in that case you can think that if you give current, it may give a cell reaction. When you reverse it, it may not be the exact reversed reaction taking place within the cell. So, such cells we can say to be irreversible. Next, let us see what do you mean by a reversible electrode. Reversible electrodes are those electrodes which constitute a reversible cell. We know that a cell constitutes two electrodes, an anode and a cathode, and this anode and cathode, if it is in a reversible condition or if it is constitutes a reversible cell, we can call that electrode to be a reversible electrode. So, reversible cell means the electrodes are also reversible. Next, we will see there are the types of reversible electrodes. Reversible electrodes are generally classified into three. They are electrodes with respect to reversible with respect to anions, and those reversible with respect to cations and redox electrodes, or we can call them as oxidation reduction electrodes. So, again there are three types of reversible electrodes. We will see each of them in detail. First one is the electrode reversible with respect to cations, and in this category you can have two types. that is metal ion type and gas electrodes. Metal ion is the one you have seen in the Daniell cell, that is you can have zinc dipped in zinc ions. Remember, there is a bar to show that these are two phases, one is in the solid phase, one is in the solution phase. Now, since the zinc ions are in aqueous phase, I will just put it in bracket aqueous to show that this is the solution, it is not in the solid state. Okay. And zinc is actually in the solid state. So, either you can put it as zinc or you can put it as a S in bracket to show that it is in the solid state. Any other metal, you can take copper dipped in copper ions, again I put it as aqueous. Otherwise, it should be mistaken for, it can be either a copper sulphate in the solid form, it is not like that. It is in the solution form to show that we mention it as aqueous. So, any metal in contact with its own ions is taken as a metal ion electrode, and such electrodes will be reversible with respect to cations, because metals they provide cations and we can assume that it will be reversible with respect to cations. So, for example, I am going to write an electrode reaction of zinc. Now, one more point to be considered, according to IUPAC convention, you can have electrodes to be written in the form of reduction, you cannot show it as oxidation. Now, if you are considering the electrode in a cell, you can show both oxidation form and the reduction form, provided those electrodes I am showing it as a electrode reaction within a cell. If I am showing the electrode reaction single electrode reaction, that is I am going to show only the electrode, nothing connected with the cell. You have to represent that electrode to be in the reduction form. So, if I have to show the electrode reaction of zinc, I have to put it as zinc 2 plus, which is in the oxidized state, then it takes up 2 electrons. Again I am mentioning that zinc 2 plus is in the aqueous medium. Okay. It gives Zn solid. Okay. So, what I am showing here is this is the electrode reaction of zinc metal in contact with zinc ion. Here zinc ions get reduced to give zinc metal. In a similar manner, if I have to write the electrode reaction for copper metal in contact with copper ion solution, here again reduction form, we know that copper 2 plus is in the oxidized form. So, I have to take copper 2 plus in the aqueous state, which will take up 2 electrons, then form copper solid. So, this is the electrode reaction for a copper metal electrode. Okay. Now, do not think that any electrode should be always written with 2 electrons. You can also have electrodes in which we need only a single electron, for example, silver, which we have already shown here. See Ag, Ag plus. Here Ag plus is the oxidized state, has to take up only a single electron to give Ag solid. Okay. So, whatever be, if I am showing a single electrode reaction, I have to represent it as a reduction reaction. So, here I have been discussing, that is an electrode reversible with respect to cations, and in that category the metal ion electrodes. Now, one more point to remember, that is when we put this reaction like this, like I have taken copper combining with 2 electrons to give copper metal. Now, why do we say this electrode to be reversible with respect to cation? Cation in the sense that is copper, here cation is copper, this is the cation. Now, this cation, just think that if the cation concentration is increasing, automatically this will shift towards the right, or you can say the forward reaction takes place. Now, if there is a decrease in copper ions, what will happen? Naturally, copper goes into copper ion. So, this is the concentration of the copper which determines whether the electrode reaction occurs in the forward reaction or in the backward reaction. So, we can say this electrode is reversible with respect to its cations, and copper in the sense it is 100% pure copper, and for that we cannot mention the concentration, and therefore, you can say this electrode, the potential of the electrode, that is what we see how much the redox reaction is taking place. The potential of the electrode depends upon the concentration of the cations, and such electrodes, they are reversible with respect to cations. Now, another variety we can, for in general you can also mention that a general electrode reaction with a valency Mn plus, here we were dealing only with the valency of 2 and 1. Instead, if the valency of Mn plus, okay, which is in the aqueous medium, can take up, so it has got a valency of n, so it can take up n electrons to form metal solid. This is a general form. You can put it for any other. If I am taking aluminum for example, aluminum has got a valency of 3. Aluminum ions in aqueous medium can take up 3 electrons. So, n stands for the number of electrons required to neutralize the cation. So, you will get aluminum which is in the solid form. So, this is first type. Again you have another type which is reversible with respect to cations, and that is a gas electrode. Gas electrode means, here we have, first we have seen metal in contact with metal ions. Instead, here we are having gas in contact with an electrolyte which contains the ions of the gas, and one of the easiest and the best example is the hydrogen electrode. This is known as hydrogen electrode. You can see the hydrogen gas in contact with hydrogen ions, and there is some difference because you have to put an unattackable metal, because when you are having hydrogen gas you cannot derive, how will you take out the electrons out of the solution? Once if there is an oxidation or reduction, whatever is taking place, electrons cannot travel through the solution, they can travel only through a metal. So, in this case what we do is we take an unattackable metal which is usually platinum. So, we take platinum. So, whenever you have to put a gas electrode, you put platinum comma hydrogen gas. So, this acts as the substitute for the metal part in a metal electrode, and then we have a solution in which you can have hydrogen ions, that is H plus. You can take any acids which can furnish H plus ions. Okay. So, this is the hydrogen electrode. Now, here what happens is, I will write the electrode reaction. Now, how to write the electrode reaction is easiest way, you check both the sides. Here you have H plus ions, and that is oxidized state, and H2 is the reduced state, and we have to write the expression in terms of reduction. So, I will take H plus ion first, which is in the oxidized state, only to that you can add electrons. So, here H plus takes up an electron, okay, giving hydrogen gas, and this H plus I have taken from an aqueous media, and here you can see that to balance it I have to put it as half H2. You can write it in both ways, or you can put it as like that, 2 H plus will take up 2 electrons to give hydrogen gas. In both ways it is correct. So, here we are representing a gas electrode. Now, how this is set up? That is, you have to bubble hydrogen gas to a solution which contains hydrogen ions, and in that solution I will be dipping a platinum electrode, and from this platinum electrode I can connect it to external circuit. So, this is how a gas electrode is set up. So, we have two types here, one is metal ion type, and the second one was gas electrode. You can have another type of gas electrodes too, but in this case I have taken only hydrogen, which can provide H plus ions, that is cations. So, these two are reversible with respect to cations. Next we are going for the second type, that is electrodes which are reversible with respect to anions. Okay. So, here again first one is a gas electrode. This is also gas electrode, and remember you have to add additional, that is an unattackable metal which stands for transporting the electrons from the electrode. So, here platinum does not take place any of the electrode reaction, because you know that it is an unattackable metal. Now, here again to write the electrode reaction, check both the sides. You are having chloride ions as well as chlorine. Now, in this case, which is the oxidized form? Oxidized form is chlorine, and this chlorine you can put it both ways. I can put it as half chlorine will take up an electron and gets converted into chloride ions in the aqueous. Now, this is again a reduction reaction. Chlorine is taking up electrons and getting converted into Cl minus, that is chloride ions. Here you have to see that I can put it as half chlorine, then there is only one electron. Instead, if I take chlorine Cl2, it is a bimolecular compound. So, if I take 2 chlorine, I have to put 2 electron, which in turn will give you 2 Cl minus in the aqueous form. In whichever way, just like in case of hydrogen, you can put it either way. Anyway, it is the correct way of representing the electrode reaction. So, here we are having chlorine gas, again just like hydrogen. Yeah, we are having chlorine gas bubbling through a solution which contains chloride ions. Now, the chloride ions you can have it from, you take HCl, you will get chloride ion, you get sodium chloride, KCl, all these has got chloride ions. So, any of these electrolytes you can take which can have or furnish Cl minus ions, you take that and then bubble chlorine gas through it, insert a platinum wire and it makes a chloride electrode. So, here again you can see if the chloride ion concentration is changed, okay, what will happen? There will be a change in potential in this electrode cell, just like in the case of cations. In this case, it is the anions. So, it depends upon the potential, depends upon the concentration of chloride ions, or you can say this electrode is reversible with respect to anion. Next type is, that is two types we have, one is the gas electrode, the other one is a very important one, because we have some standard cells and reference electrodes and all made from such type of electrodes. This is metal, a metal insoluble salt, which is again contained in a solution which contains an anion in common with the metal salt. So, you have to take a metal insoluble salt, it should be insoluble, and this insoluble salt should be kept in a solution, and that electrolyte solution should have an ion, that is the anion, which is in common with the insoluble salt. Okay. So, here the first example is silver chloride electrolyte. The name is silver chloride electrode. So, here the insoluble salt is silver chloride, the anion is chloride, and therefore, this should be dipped in a solution containing chloride ions. The chloride ions again usually what we take is the KCl solution. Here you can have K plus and Cl minus ions. So, it contains chloride ion, and therefore, this can be considered as the silver chloride electrode. Now, silver chloride electrode, again you have to check for how can we write the electrode reaction? The electrode reaction, I told you, it should be always in the reduction form. So, we will check both the sides. One side we have silver chloride, the other side we have chloride ions. So, which part here? Silver chloride means this is Ag plus and Cl minus. Okay. Then one more factor, in this case we have to consider, whenever you write an electrode reaction, there should not be any extra element other than what is shown in the electrode. So, how are you going to represent an electrode? The electrode reaction should contain only those elements, any other elements other than that should not be shown in a electrode reaction. So, here we have silver chloride salt, okay, that is Ag plus and Cl minus, and again the ion is, you are having Cl minus ions, and then you can have Ag solid. These are the things which are involved in the silver chloride electrode. Now, what I am going to do is, I have to represent as a reduction reaction. Now, Ag plus is the only thing which is in the oxidized state, and Ag plus it is not occurring as such, it is in the form of AgCl solid. So, what we have to do is, the electrode reaction will be in the form AgCl will take up electron, like how much electron it will take, because Ag has got a unit positive charge. So, it can accept 1 electron. So, that will take 1 electron, it reduces Ag plus to silver metal, no matter, because silver is already there in the electrode mentioned. And what happens is, this electrode joins with Ag plus ion and the chloride ion is left out. So, that will be given Ag plus Cl minus, which will be in the aqueous form. That also is there in the electrode, because we are having an aqueous solution of chloride ions. Okay. So, here just check that for metal insoluble salt, we have to take the salt, because in that only you have the cation, to which we can add an electron. Okay. So, Ag plus will take up the electron, and in that the silver metal ion gets reduced to silver metal and the chloride ion is left out. Hope it is clear. Now, we are going to a similar electrode, which is also known as calomel electrode. The name is calomel electrode. Calomel is a name given for mercurous chloride, He2Cl2, which is mercurous chloride. So, here we have mercury in contact with its insoluble salt known as mercurous chloride or calomel, and again you can have the anion is chloride, and therefore, you have a solution which contains chloride ions. Now, again in this case we have to write the electrode reaction in the form of a reduction reaction. Here we have done already, that is, in the case of AgCl we added electron to AgCl. In the similar way, here we have to add it to the He2Cl2, that is mercurous chloride. This mercurous chloride will take up electron. Now, how many electrons? Because mercurous means each mercury has got +1, and you have 2 mercury atoms here, and therefore, these 2 mercury should be supplied with 2 electrons. Sorry, this is a minus. So, He2Cl2 will take up 2 electrons, that is each He plus ion, that is one He plus ion will take up 1 electron, the other He plus 1 will take another electron. So, it requires 2 electrons, then gets converted into 2 He liquid, and the chloride ion is left out. So, you have 2 Cl minus in the aqueous form. Again, just check all these are there in the electrode which I had represented. See, mercury is there, mercurous chloride is there, chloride ion is there, nothing extra, everything is represented as the electrode. So, that makes another electrode which is reversible with respect to anions. So, we have seen two, that is metal insoluble salt type as well as gas electrodes, which are reversible with respect to anions. Next, we will see the third type, that is oxidation reduction electrodes. Oxidation reduction electrodes are those electrodes in which we have an electrolyte which contains two oxidation states of the same element existing in a solution form. So, we all know that you can have the same element with two oxidation state until unless they are those elements which are capable of showing variable valency. And here we can see that the taken ones are ferrous ferric, stannous stannic, all these elements they can exist in two oxidation states. Okay. So, what we do in this case is you just take a solution which contains a mixture of ferrous and ferric ions, dip a platinum wire into the solution, that is an unattackable metal to conduct electricity outside or inside, whatever it is. So, for that you insert an unattackable metal, and usually that is platinum. In both cases, that is, you can either take ferrous or ferric or stannous or stannic. This makes a redox system. So, in the redox system, I am going to insert a platinum electrode or platinum wire, you get the redox electrodes or oxidation reduction electrodes. Now, here it is very easy to write the reaction, because here we have two ferrous and ferric. We have to write it in the form of reduction, and therefore, find out which is in the oxidation state, that is usually it is the ferric. So, the ferric ion in the aqueous state will take up how many electrons, because it has to get converted into only Fe2 plus, nothing other than that. You cannot make it into iron. Now, why is it so? Just because you do not have iron in the electrode, you are having either ferrous or ferric. So, you add just one electron, it gets converted into ferrous. So, there is a reduction, that is ferric is reduced to ferrous in the aqueous state. So, this forms a oxidation reduction electrode. In a similar way, you can have the second type, that is, here again you have SN2 plus and SN4 plus. It is obvious that SN4 plus is in the oxidized state. Now, it has to add up 2 electrons, and that will give you SN2 plus, and both these are in the aqueous state. So, we have another type of redox electrodes. You can have any such type, cerium, you can have serous and ceric forms, any type you can have. You just dip, you take the mixture of these two, dip a platinum wire into it, you can set up a redox electrode. So, in this class we have been seeing reversible cells. Reversible cells, as you know, that it should satisfy conditions of reversibility, that is when EMF is greater, when EMF is lesser, or when we say when the EMF is equal to the external EMF. All these conditions has to be exactly satisfied, otherwise we cannot call that to be a reversible cell. Then we have been seeing reversible electrodes. Reversible electrodes are those electrodes which constitute a reversible cell, and these electrodes, they are further classified into 3, that is, we have been seeing the 3 types, that is those electrodes which is reversible with respect to cations, that which is reversible with respect to anions, and also oxidation reduction electrodes. And in all these you can see that the reversibility depends upon the concentration of the ions. Whichever the ion is concentrated, depending on that the reaction will take place, and therefore, they are reversible with respect to those conditions. So, that is all. Thank you.